Hello everyone, I am Pushpita Chandra. I am a PhD student at IIT Delhi under IIT Delhi and University of Queensland joint PhD program. So I am a TA for this course, Fundamentals of Attosecond Science and Technology. So today's plan for the class is basically to discuss February Italian in a brief and in a concise matter, and then discuss some question and how to approach, how to solve it. So let's begin. So basically, we know that in this class, it is being like discussed as a this course. The February period has been discussing, like professor has been discussing February period in the course because to generate ultra fast pulses, we need laser, and the February period it alone serve as a perfect laser cavity. But Febripero can also be used as a in a spectroscopic or filter in a like it can it has a good resolving power that it can resolve to like very close wavelength. So that is I'll discuss some like question about that also. So first, some recap. A naught or E naught has been used, like professor has used E naught in the class, but if you like use Ajay Ghatak as a reference book for only the February part, we can see they have used A naught. So that is basically complex amplitude of incident wave. T1, it's not or. So that is called amplitude reflection or transmission coefficient. Incident from N1 medium to N2 medium. So basically here N1 and N2 are refractive index. So N1 medium means a medium which has a refractive index of N1. And R2, T2 is simply the same thing, amplitude of reflection and amplitude reflection and transmission coefficient when wave is incident from N2 to towards N1. basically so this is the diagram for multibeam interference. So the light is incident is not normal. Light is not being incident normally on the surface, and here it is not Fabry-Pérot at all. First, it's because it's the in Fabry-Pérot there is only two reflective mirror, and in between there is only air. But here this whole slab is of the same material. But it is basically whatever reflectivity and transmittivity equation we have discussed in the or we have seen in the class, that's gonna be same. So this is theta 1, sorry, that is theta 1 or theta I, and this is theta 2, which is the refracted angle between inside the medium. And this is how, like, if we move that if any ray come parallel to AB, then these rays are transmitted rays and these rays are reflected rays. They will, like, if you like it, instead of AB, if there is another ray parallel to AB, then the point P will move along this circle, and at that transmitted site, this point, let's call it D. D will move along the circle. So round trip path difference here round trip path difference that can be denoted by delta 2N2H. This is the thickness of the slab H. It can be denoted as D also, uh, to N to H cos theta 2. So the phase difference in a round trip or round trip phase difference delta would be 2 pi by lambda 2 nt or lambda naught H cos theta 2, which will be 4 pi n2 H cos theta 2 by lambda naught. Now, reflectivity for Fabry-Pérot etalon N2 is 1 as it is AR only. And this is Fabry etalon. Both are basically reflecting surface. This is N is equal to 1, this is equal to 1, this is equal to 1. So R1 is equal to R2 and T1 will be equal to T2. So for the reflectivity, to know the reflectivity of Fabry-Pérot, we have to do some calculation. First, I have written that small r and small d are the amplitude reflective amplitude reflection coefficient and amplitude transmission coefficient. And reflectivity of at each interference is given by R, which is equal to R1 square to R2 square. And transmittivity each interface are given by T1, which will be T1 into T2, which is basically 1 minus R. Now in the class, professor has already shown what is the transmittivity of the Fabry-Pérot etalon, and that is basically 1 plus f sine square delta by 2, that is transmittivity of Fabry-Pérot etalon. Similarly, if we made the calculation like the transmittivity, we will get some calculation for it, so that you can understand. It reduces to this kind of equation. So if you solve the thing e to the power I delta as 1 minus cos delta and all those things, in all this value, it will get that reflectivity is basically 1 4 r sine square delta by 2 by 1 minus r whole square plus 4r sine square delta by 2. You can write as f sine square delta by 2 by 1 plus f sin square delta v. So r plus t is equal to 1. We don't have the for ray at the Fabry-Pérot boundary. So we know if it's called coefficient of fineness. Fix is basically 4r. This r is the reflectivity at the interface, at each interface, equal to 1 minus r whole square. So I write another form of f. I want to first write what is T max. T max will be 1. So the one when it will be 1, when delta will be 0. So T max is 1 when delta equal to 0, and T mean is delta is equal to delta by 2 is equal to 1, or sorry, delta by 2 is 2m pi. That is when two is equal to m pi, delta would be 2m pi. That is get T max is equal to 1, and it will be 1 delta by 2 would be 90 dB and all. Then T minimum will be 1 by 1 plus F. So we can write F as T max minus T min by T min. When you put this value in this thing, you will get F basically. So coefficient of fineness can be written as this thing also. And also the function 1 by 1 plus F sin square delta is called any function. It will also be. So if you want to like picture T, you need to picture like AD function. So this is the transmittivity, and the reflectivity of the interface would be this. So you can see when we are writing transmittance in the vertical axis, we will get this kind of spikes. Okay, but when we are writing reflectance on the vertical axis, then at the position of the spikes, we'll get dip here. So both the picture define the same thing here. So see, f is equal to fineness when the coefficient of fineness is 200, we will get sharp spike, and here corresponding to we will also get sharp dip. Now we want to measure the FWHN full width at half maxima of the peak. So it gives us the measure of sharpness. That it is how rapidly the irradiance drops either side of the maxima is half of the full maximum. So equal to 1 when we get maximum. So we know that when delta is equal to 2 and pi, we get T is equal to pi. So basically delta is path difference, or sorry, delta is a vertical phase, so that is by lambda into this delta. This is equal to 2 and pi. This is the condition of transmittance. So basically the condition is till the lambda equal to m. So lambda should be delta by m. And we know lambda is 2n h cos theta 1. If normal incidence then theta 2 is equal to 0, cos theta is equal to 1, and for Fabry-Pérot n2 is equal to, sorry, n is equal to 1. So it is basically 2h by m. So to get the maximum fringes, the h should be m lambda by 2. Here we can put m in value 0, 1, 2, and 3, and such sort of. Now, should be m lambda by 2 to occur the maximum. So now we will go to FWHM. So now we suppose that for FWHM, T has to be half. And at delta is equal to 2m pi plus minus delta by 2, we get that T is equal to half. So T is equal to half means 1 plus f sine square delta by 4 here. We put delta value here. First put square delta by 2 is equal to 2. Now we put the value 1 plus f sine square. So here it will be m pi plus delta by 4. We know inside of sine m pi, if we put m pi, the sine function remains sine. So it will become delta by 4 is equal to 2. So from that we get sine delta by 4 is equal to 1 by root f. So delta by 4 sine inverse 1 by root f. So when f is, so this is that half with full maxima FWHM, where it has been written as gamma, but we can read as delta lambda, delta. And so when f is very large, sine inverse 1 by root f is so small of 1 that sine inverse 1 by root f becomes 1 by root f. So from that we get the full width half maxima is basically 4 by root f. So it is basically 2 into 1 minus r by root r. So this is delta is equal to 2m pi, we get maxima. So at delta maxima minus delta 1 by 2 delta 1 by 4 both will give delta by, okay, delta by 2 and this will be delta by 2. So at delta max minus delta 1 by delta by 2, we'll get like half of the maximum transmittance, and delta max plus delta 1 by delta by 2, we will get the half of the transmittance. So it is basically delta by 2. So that is FWHM. And then we find the another parameter which is finesse, which is given as RBF. Like this is the ratio of shape separation of hyperson maximum, or we can say F is of separation of adjacent maxima. Right. divided by full width at half maximum. So if you put that thing we get pi root f by 2. Also, I have also mentioned that uh, the tubular Italian has a great resolving power. So that power equation, you can go to the any book, the Hecht uh, optics by Hecht and also optics by Ajay Bhatta, we will get the calculation. Uh, the calculation is slightly different in two books, but they basically are the same. So the resolving power in frequency domain, this is the minimum resolvable bandwidth, is pi h nu root f n by c, and in wavelength manner it's called I n h root f by lambda. So what is basically resolving power means? So resolving power means if two chromatic lights, not monochromatic lights, the source has two lights, so two wavelength, they pass through the etalon. So what should be the resolving power, or like how the etalon can separate two peaks? Two peaks will be separated when that is half maximum. So, and this is minima. So the two peaks will be resolved perfectly when that half intensity point of one peak falls on the half intensity point of another. So here we see that half intensity point of this peak and falls on the half intensity point of that peak. So if they does not, or if they would have crossed like this, follicular Italian cannot resolve two peaks. So resolving two peaks means they intersect each other at half of maximum. Mm. Now there is another thing called the flatness of the coated surface. So I have already shown that for maximum lambda delta by 10. So this is basically 2h is normal incidence and n is 1 by m. So h has to be m lambda by 2. Right. So in order to have a sharp fringes, the coated surface should have been very parallel to high degree of efficiency. Okay. And also that distance between two plates should kept at a multiple value of lambda by 2. Okay. And it is said that they should not the parallel plates should be flat within about lambda by 50 range. So that means from lambda by 2 you can like move the coated surface lambda by 50. Even if you move by lambda by 20, then like I'll gonna like give you an example. In that example, they are using 5,000 angstrom wavelength and 4,999 into 98.98 angstrom. Their maxima will fall on the same place. If you move parallel plates by lambda by 20 distance of what it should be, and you cannot resolve the two peaks. So first, let me write question. Example 1. This example is taken from the book Ajay Ghatak, book by Ajay Ghatak, professor. So as an example, we assume an beta long with n2 is equal to 1, h is equal to 1 centimeter, and f is equal to 400. That means r is equal to 0.905. So basically they have 90% reflectivity. So in figure, we have plotted the intensity variation with theta for lambda 0 is equal to 5,000 angstrom and 4,998 Okay, that is 9 angstrom. So you can which fringe patterns we'll get. So first should get the picture. So this is the picture we need to prove, which here it is already written, which lambda is which one. And this is the actual fringe. This is the actual fringe. So we know that delta is 4 pi lambda naught into h cos theta. For maxima, this delta is to be 2m. So basically cos theta 2 is m lambda naught u into h. So for lambda naught is equal to 5000 angstrom, cos theta or theta 2 is equal to cos inverse m 40,000. So the right fringe would be, we know the brightest would be at cos inverse 0. So theta 2 is to be 0. Should be 4.405 and 5.7 cos me do. N equal to 40,000 3999. So first we will get one cosine plus one equal to C. So from one m should be 40,000. Then after 40,000 we need to get one mode less, so that would be 39,999. For that we get theta 2 is 0.405 and 3998. That's how we get. And for lambda is lambda naught is equal to 499.98 angstrom. Theta 2 would be cos inverse in 2000.16. So again, theta 2 would be the bright fringes will form at 0.162, 0.436, and 0.595. This corresponds to, why there is no zero? Because the m is full number. It cannot be 40,000.16. It start with 3999 here. So that's why there is no theta 2 is equal to 0 for lambda naught is equal to 4999.98 angstrom, as m cannot be 40,000.16. That corresponds to 39999, 3998, and all those things. So that's why this peak is corresponding to 5,000 angstrom, and this is 49999.98 angstrom, and this is the maximum difference between them. That's why the central ring, see, this is the central right for 5,000 angstrom, and this is the central right for 4,999.98 angstrom. After that, the spacing between two fringes is less. So you can see one we get at 0.405, another 0.436, one at 0.573, another is 0.595, and so on. So and now, if we move the parallel plates, or the distance between the parallel plates, or we can say age is increased by lambda 20, what will happen? So now age from 1 centimeter to, it could be lambda by 20, which is between 2.5 into 10 to the power minus 6. For lambda, we have taken 5,000 angstrom. Excuse me. So for lambda naught, 5,000 angstrom, theta 2, because inverse m 0.16. The bright ranges was for lambda naught 5000 angstrom will fall at 1.128 degree, 0.425 degree, 0.587 degree. But as 2.5 into 10 to the power minus 6 centimeter is less than not multiple of lambda by 20 for lambda is equal to 49998. Sorry, this is also 998 angstrom. Its bright fringes will not move. Is equal to 4. Will not move. So fringes will overlap. This is less than lambda by 20 for this thing. So it will not affect the wavelength or will not affect the bright fringes due to the 4999.98 angstrom, but it will affect the bright fringes for 5000 angstrom. So they will start overlapping. Then we will not be able to see the two different fringes, or the resolving power of fabricator will diminish. Now another example. Is of hormone patient 0.8. Basically, y is equal to 80%. So the finesse would be pi root r by 1 minus r. That is pi root r is 0.8. 1 minus 0.8. So if we put all those things, it will be 14.04. That is the thinness of this thing. Or you can put like you can calculate capital F, which is coefficient of thinness, then pi root f by 2. That will also give the same result. Now we will go to example 3. So the question is, a Fermi-Payot echelon is fashioned from a single slab of transparent material. So this is the single slab, okay, and this single slab has a refractive index of 4.5 and the thickness is 2 centimeter, and this uncoated surface have a reflectance of 0.90. So we are bombarding this so we put a echelon, it's lambda naught, which is 546 nanometer. Now we have to know the highest order fringe in the interference pattern, the ratio T max minus by T mean, which is transmittance, the opposite of transmittance basically. No, that is the transmittance. And the resolving power. So the T max is equal to 1, T mean is equal to 1 by 1 plus F. So it's not actually transmittance, it's basically 1 plus F. So let us begin. A. So we know delta, which is the boundary first difference, is equal to 2 n pi when maximum will happen, it is equal to 4 pi n d, and 4 pi n d cos theta by lambda. So here n is equal to 4.5, d is equal to 2 centimeter. So n basically 2 nd by lambda naught. Lambda naught is equal to 546 nanometer. Or here theta is not given, so we say that it is a normal sitting, so is equal to 0. Now putting this thing, we'll get for like the maximum order, highest order fringe. Like the highest order fringe is basically the center. So for that, theta has to be 0. Center. For that, theta has to be 0. So putting all this value in 1 unit, 2 centimeter, here lambda is nanometer, so we put all those things in meter. And putting all this value, we get something 3 into 3 into 10 to the power 6. This is the highest order. It would be T max by T mean. The transmittance max, which is 1, transmittance mean is 1 plus F. So that is 1 plus F. So it is 1 plus 4R by 1 minus R square. So R is here 0.9. If we put all this value, it would be 361. The resolving power is we knew that it is pi n h root f by lambda naught. We can write it as a n into s. So it will be n root f into pi by 2. So basically it is 3.29 into 10 to the power 5 into pi root over 360 by 2. So that is 9.8 into 10 to the power 6. So that is the resolving power needed. Now question number 4. So basically the question is a high light source consisting of two different wavelengths, lambda and lambda 2. The light source from this to be incident on the scanning Fabry-Pérot interferometer of the nominal length of 5 centimeter. Let the scaled transmittance through the cavity be a function of cavity length as shown in figure 5.8. This is the figure 5a. Figure 5.1b shows that the first set of dual peaks of figure 5.1a will have a smaller length scale in order to allow a closer examination. Of the overlapping peaks. What is the nominal wavelength of the light source? What is the estimate the difference lambda 1 minus lambda 2 when they have the same mode and when they have different mode? So the nominal incidence is used. So theta would be 0. The air is in between Fabry-Pérot, so the refractive index will be 1. So basically here it says that one peak is 0.05 micrometer and another 0.3, and 5B is a closer look of A. Thing is, the scale has some this different meaning, I guess, because it's this peak is at 0.3, so maybe there is some discrepancy, but we will do our calculation with respect to this picture. So we don't need to look at the different picture. So basically this question for 1A, we need to look at this picture, and for lambda 1 minus lambda 2, they said the closely spaced peaks, so we need to consider this thing. So basically here you can see that here there is 2 peaks and here also 2 peaks. So they have closed, this thing is this thing basically. So they said 2 sets of peaks. So also said the first set of dual peaks over a scale. So it is a dual scale, dual peak here, and it is a dual peak here. Only this dual peak is enlarged in here. So answer a first scale. So 2 sets of dual peak is observed at 2 different scanning distance. So let us say at okay. So D1 we can say is a nominal distance plus some distance, and D2 is nominal distance plus some distance. Okay. So this is change in cavity length. So when we minus D2 minus D1, D0 will be gone, and the delta D1 delta D1 so we find delta D2 is 1. Okay. So for delta 1, this is the phase difference for d1 would be 2 by lambda naught 2n g1 cos theta. So here nominal incidence will be assumed. So theta is equal to 0, n is equal to 1. So it would be 2 pi lambda naught 2 d naught plus delta d naught, which should be equal to 2 n pi. For delta 2 also we write the direct thing 2 d naught plus delta d2 will be 2 n pi. And it should not be n pi because if this is order of m, that has to be n plus 1. So this is 2 into n plus 1. Now we subtract. So it comes around to 5. Okay, so 2 d naught plus delta d2 equal to lambda 1 n plus 1 and minus 2 d naught plus delta d naught. So here minus 1 naught and that will give us 2 into delta d2 minus delta d1 for theta is equal to 0 and has to be 1. So this becomes lambda naught. So this is 0.3 minus 0.05 lambda 0. So lambda 0 is 0.5 micrometer. So nominal load is 0.5 micrometer. This is the nominal area. So that is big. What means 0.5 into 10 to the power minus 6. So that is 500 nanometer. So basically the nominal wavelength is 500 nanometer. Now personally like to resolve those two wavelengths, we will get that the resolve, they are very closely spaced in like if it is in micrometer range, that should be in nanometer, like 1 nanometer or 2 nanometer. So for that, we'll start from the equation 2 into delta d on right minus delta d on left. Here, this is left and this right minus at 0.05 and this is at 0.048. Here it was n lambda, but in this calculation it will be n delta lambda. say that n is equal, n is same for both the would be delta lambda by lambda naught is equal to delta d by b into will be cancelled. So delta lambda is equal to lambda naught into delta t by d. So d has been given 5 centimeter. So 5 into, we want to see those things in micrometer. So 5 into 4 micrometer. Delta d is 0.05 minus 0.048. And we know lambda is equal to 0.5 micrometer. So this would be 2.0 into 24 minus 8. So it is 20 minus, okay, so it is 2.0 into 10 to the power minus 14 meter. So 2.0 into 10 to the power minus 5 into 10 to the power minus 9 meters. So basically 0.00002 nanometer. So the Gabriele Italian can resolve this kind of order. Now, if both mode are not M, so we say that for left mode it is, for left fringe it is M mode, for right fringe it is N plus 1 mode. So that is delta D L equal to N lambda 1. So N lambda 2 plus Z basically. So we will go to the now is delta D 1 R for that is N1 plus 1 lambda. So now subtract the two result, we get two minus N1 delta 1. So we assume that lambda 2 is lambda, which is 1.5 micrometer, and M is visible to do not lambda. So putting all this value, we get the lambda equal to lambda naught. All these values we get 2.5 into 10 to the power minus 6 micrometer. So then 2.5 into 10 to the power minus 3 nanometer. So basically, coming 0.025 nanometer difference will be there in two wavelength. So now the last question for today. I question to discuss, but I'll discuss the next day. So the question is basically very easy, but with that we need to incorporate very trivial thing, not physical concepts. It's very easy. Estimate the coefficient the coefficient of fullness F and the Finney's curve and the mirror reflectivity to account for every narrow cavity with the joints with curve shown in picture. Okay. So we see the T max is 1, T mean is 0.5. And free spectral range is 2 pi. And this is given as like 1.5. This thing is a WHO. So we have seen from picture T max is equal to 1, T mean is equal to 0.05. So I have already proven that the coefficient of units can be written as T max minus LB by T because T is 1 minus 1 by 1 plus F by 1 plus F. That will give us F. So T max is here 1, T min is 0.05, T min is 0.05. So this is 190. Then we go to coefficient. We got finesse, coefficient of finesse. Now we want to calculate finesse. Okay. So that is I root of right 2. So that is almost 5 root and 10 by 2, which is 6.8. Also, we can calculate that thing by free spectral range by FWHM. So here, free spectral space is 2 pi. This is the free spectral space. And this is, which is 1, is the, or we can don't say that is 1. It's 2.03 and another is 1.11. So that can be written as a WHM, which is 2.03 minus 1.1, 6.8. So both words give us the same rate, right? Now we need to calculate mirror reflection coefficient. So it's 5 so R is equal to R square. R is reflectivity at coefficient small r is R square. So I'm calculating from this pi small r divided by 1 minus R square is equal to 6.8. We could have put it here also. It would give us the same result, but this term would have been, this is square, then we'll break the square, then we will get capital R square, that means small r to the power 4, and that will be complicate the lives of all the stakeholder. So here we get another equation. Okay. But take only the and that would be 2.80 almost. Today, examples and how we can resolve lambda by Federico Vitala and how we can measure like calculate the finesse, coefficient of finesse, reflectivity and all that. So that's for today, and I'll discuss 3 more questions in the next day, and I hope. Okay, and another thing I want to show, that is what is the experimental setup in the interferometer, which is this one and this one. So basically you can see where they showed source here and where the focusing lens, and they focused all the thing. So basically for focusing lens, what it works as a when this is a broad source, this is the lens, and only one ray will be focused here, and they are reflection and they are transmitted. So this all transmitted ray, remember we add all the transmitted ray and call it transmitting. So basically this focusing lens is combining them. This is the one point. If you now we are getting a point, we will not get a fringe. We will get a fringe even when we use lens. If we move the lens, here it was shown like that. But here is lens. Now, if we change the position of the lens or move the lens, we will get a fringe. Have the whole fringe back. We don't need a focusing lens. If we remove the focusing lens and put the screen here, we will get the whole fringe pattern at the same time. And this is the fringe pattern we will get. Questions will not that hard, as I have like discussed most of the question. But these questions are also not hard when you understand what you want to do. They are basic mathematics. And you have the equation, just put the formula there. And maybe you will think that week 3 assignment has some question which hasn't covered in week 3 lectures. I'll request you to go to the week 4 lectures also. Some of first 2 or 3 lecture will help you understand the stability of cavity and all those things, and help you solve the assignment. The assignment is not that hard, but if you know, then then it is easy. Otherwise, you will know how to know which resonator is more stable and which is not. So that part I have not covered because the professor has already covered one of the lectures which has been clustered in week 4. Please go through that. So thank you. This is for today.